Hey guys, welcome to my video on sigma notation and Riemann sums. So eventually we're going to be talking about what this crazy looking formula means. If you've never watched any of my videos before, I recommend you pause and try the examples when prompted, and there are always free guided notes available. So this is kind of a tougher topic, so I actually have some extra example videos on this, but hopefully this will be enough to kind of get the idea planted in your head. And this is one of my favorite topics in Calc 1, so I'm super excited to tell you about this. So before we get started, you should already know a little bit about sigma notation. So like these rules that I'm showing you here, you should have these written down in front of you. It's going to be super helpful for this particular topic. So if you need to pause the video and write them down, make sure you've got them in front of you. And to kind of get us warmed up for this particular topic, where I want to start is I want to just do a little warm up where you're going to express some sums in sigma notation. So I have one here just to kind of show you the basic idea. So I've got the sum from 1 to 5. So you should feel comfortable, or you should be able to kind of muster your way through writing this out and not be surprised that this sum would be written from k equals 1 to 5, and then this would just be k for the formula that would represent this sum. So that's the first thing I want to do here. So I have just two of these here for you. I think this is going to be very helpful just to get your head kind of in this topic. So I highly recommend you pause the video, hit play when you're ready to see the solution. Okay, so for this sum, I've got 2, 4, 6, 8, 10, 12. So these are all even numbers. So I'm going to start with k equals 1 to 6 of 2k. And so if you think about this, then this will go 2, 4, 6, 8, 10, 12. So that'll get me exactly what I need to have. Okay, so this other one, so this is a alternating sum. So the one thing you've got to be a little bit careful about is, so this is going to go from 1 to 4 because we have 4 terms. So it's going to be -1. So you just want to make sure that however you set up this notation, the exponent on this -1 is going to allow the first term to actually be positive. So this is going to be k plus 1 in this exponent here. And then I have to also make sure I've written this in such a way so that I have all odd numbers. So let's see. This is going to be 2k minus 1. So here's the sum. So if I plug in 1 into this, so this will give me 1 minus 1, or sorry, 2 minus 1, so that'll give me 1, and then this -1 to the 1 plus 1, that'll end up being positive. So this will get me exactly what I need for this particular sum. So if you don't feel very comfortable with these, I would recommend just kind of checking out some of my other videos about sigma notation just to get more comfortable with it, because you've really got to kind of understand the basics of working with sigma notation and be very comfortable working with some of these formulas. So the next thing that I want to do is I want to refresh your memory on doing Riemann sums. So I've got this function 4 minus x squared from 0 to 2, so I've already graphed that. And I want to divide this into 4 subintervals, and I want to do a right endpoint sum on this. So this should be another thing you feel comfortable with doing. If not, you're going to want to go back and review some of that. You want to be just kind of strong and familiar with these topics before you start this. So if I am creating my 4 subintervals, so there I'm dividing it into half, and now I'll divide everything into fourths. And so from here, so I need to take my right endpoints. So I just want to visualize what that looks like. So I'll take this right endpoint over here, and I'll just draw over this way. This right endpoint is going to dictate the height. This right endpoint is going to dictate my height, and then this one. And so from here now I can actually figure out the height of all of these rectangles. So since this, since I need 4 subintervals, if I wanted to figure out my width of my rectangles, so remember we called that delta x. So this is going to be calculated by 2 minus 0 divided by 4. So we probably knew this just by looking at this, but the width of each one of these rectangles is 1/2 or 0.5. And if I just want to note what these endpoints actually are, so this one is 0.5, this is 1, this is 1.5, and this is 2. So I just need to know what are these heights of these rectangles. So basically I need to plug these endpoints into the function. And I'm going to do that by using a table. So let's see, I've got kind of all of this already organized over here. So I went ahead and calculated all of this for this. for us. You might want to just take a second to write this all down so that we can just kind of move on to the next part of the calculation. So pause the video if you need to, just write these values down. And now what I want to do is I want to actually do this right endpoint sum. But now here's kind of the thing I want to put in your mind. We're going to do the right endpoint sum, but then eventually what we want to do is we want to represent it in sigma notation. So if we just think about how the sum is actually calculated, so I'm just taking the area of each one of these rectangles, right? So the width of each rectangle is going to be 0.5, and then I multiply that times the height. So if I take 0.5 times the height of the first rectangle, so I know that that's 3.75, and then I take 0.5 times the height of the next rectangle, which is 3, and then I have 0.5 times the height of the next rectangle, which is 1.75, and then 0.5 times the last one, which we know is 0. We can even see that visually, so that's not going to throw us off. So this should be something you should understand, kind of the basics of this calculation. And now here's the part where I actually want you to think and pause for a second. Can you represent this sum in sigma notation? I'll give you a hint. You're going to have to actually use the function as part of your notation to figure out how to represent this. So I want a nice sum. I'll even get this started for you. So obviously each part of this is calculated. So we have just 4 parts, so I need to go from 1 to 4. Obviously the first part of this is 0.5. How do you model the heights of this? So I highly recommend you pause the video and you actually play around with the formula to see if you can figure this out. Hit play when you're ready. Okay, so if I want to have a sigma notation that actually is going to give me these heights, so I have to actually use the function. So I'm going to go ahead and write down f, but f of what? So I need to take f of basically each one of these endpoints, and I have to use my k to get me from one endpoint to the next. Now, I know that each width is 0.5, so really as I go through this iteration, I just need to go up by 0.5. So this whole interval is starting at 0, right? So I could start at 0, but then I take 0.5 and I multiply that times k. All right, so you've totally got to wrap your head around this and figure out kind of why did this actually work. So 0 is the starting point of this interval, but I'm doing a right endpoint sum, right? So because this is a right endpoint sum, if I just left this at f of 0 plus k, this wouldn't make sense in this case. Because if you think about plugging that in, so if I just did like f of 0 plus k, so think about what would happen for k equals 1. This would give me f of 1. That's not the endpoint that I want, right? I wanted to make sure that this ended up with this endpoint. So I have to make these adjustments in this sum, and I kind of play around with it. So I start here at 0. Each interval is this 0.5 width. So if I plug this in, this won't start me at 0. I have to plug in 1 for k. So this actually gives me 0 plus 0.5, right? Because 0.5 times 1 is just 0.5. So this will get me f of 0.5 and set this particular height. Then when I go to the next one, that'll get me to 1, and then 1.5, and then 2. So this would actually be the way that you represent this. So this is kind of the thing that I wanted to do here. So I want to keep playing around with this idea. So now what I want to do is I want to do this in 8 subintervals, still using the right endpoint, but I want to write that once again in sigma notation. And just to help you out, I will even write out just what the endpoints are. Okay, so I went ahead and calculated just all of your right endpoints. So what I want you to do is the same thing again. So now we've got 8 subintervals, so the width of your rectangles changes. So can you represent kind of this right endpoint sum in sigma notation? So you've got this in front of you. Go ahead and play around with it. When you think you have figured out the sum, go ahead and hit play. Okay, so I'm just going to write out all the pieces of the sum first, so I'll just do that. Okay, so there's the whole actual sum written out. So again, I don't actually care what the sum equals, so I've kind of talked about that at length, how to actually compute all of this. All I care about is how could I actually write this now in sigma notation. And so it's kind of that same idea, right? So if you're using right endpoints, so remember you're starting on the right. So I'll just kind of mark like all those endpoints in this bright green dot that we're actually interested in. So you're not interested in the very first you're not interested in this endpoint here, right? So you're really interested in starting here, but then making this jump of this 0.25 width each time. So it looks very similar to the last sum that we had, but now I'm going to go from 1 to 8. And now my width is 0.25, and then I'll take 0 plus 0.25k this time. So here's how I can represent this whole sum in sigma notation. Okay, so hopefully you're kind of seeing a little bit of a pattern here, and I know that this is kind of a lot to go through, but it's going to help us build up kind of the next part of this. So now what I want to do is I want to think about how would I write that Riemann sum. So what if instead of telling you how many subintervals I wanted, I just want to come up with the general formula now for just n subintervals. So first let me write down just the two Riemann sums we came up with, or sorry, the two Riemann sums we came up with in sigma notation. Let me write those down. So those are the two Riemann sums that we came up with. This was the one for the 4 subintervals, and this was the one for the 8 subintervals. So just look at the actual structure of these things. So this part here, this is the width, right? And we have a general formula to get us the width. So in general, my width is this delta x calculation. So it's always just b minus a divided by n. So in this case, for this formula, this was what, from 0 to 2. So this would be kind of the general form. So here's kind of how you could get that width in general. And so if that's the width here, this is the starting point of the interval, right? So 0 was where this started, and then this is really just going up by each width. So this part here is also interchangeable. So if I want to do this now for n subintervals, then the most general formula that I can come up with would be just replacing these widths with just kind of this more general way to calculate it. So this would be 2 over n times f of 0 plus 2 over n times k. So that would be it. And then just tell me, what you want, how many subintervals you want, and then we can kind of figure it out from here. All right. So this actually then illuminates the general formula for all kind of Riemann sums and sigma notation. So what I want to do now is I want to show you the general Riemann sum for right endpoints. So remember that you're going to have a function. So you have some function f of x on a closed interval from a to b. This is kind of the whole thing. And then we usually have n subintervals. So I just want to kind of preface this formula with that information. So here's the formula. All right, so I've kind of, I guess, rearranged this a little bit, but what I want you to do here is I want you to pause the video for a moment, write this down, and just connect all of these letters. What of these letters have to do with the graph, and what of these letters have to actually just do with regular sigma notation? So take a moment, write this down, and actually stare at this. This will really help you out. So notice, so this is the start. This A is the start of the interval, right? So that comes from that A to B. And that's exactly what we did in our formula back here, right? So my interval in this whole example we were working with, I started at 0. So we still have that idea of this starting spot. So there it is. And then here I've got my width here. So I take f of this whole value, which I've got to figure out, and I basically am moving across the interval, kind of like how we were discussing with these examples here, right? So I start here and then I adjust for my width, and then I move over to this spot, and then I move over to this spot, and I just keep calculating f of each one of these points. That's what we were doing with this part of the formula here. So same idea here, just now in a more general form. And then this, you could really multiply this at the beginning or the end. So now I just have it written at the end, but it's still just multiplying all this times the width. Okay, so one thing I want to ask, how can we adjust this formula? What if, so this is for right endpoints. What's the adjustment that we would make if we want to start on the left? And maybe you want to draw yourself a little picture to like figure this out. This is a good thing to think about. So if I start on the left, so I just don't need to have that A plus all of this, right? So this will just get me to start right at A. So that's actually the adjustment that I would make in this case. So I can just plug this right in and be good to go. So I don't need to start at A and then add something to it. Okay, so now I want to add just a little bit more on to our thought experiment here. And I really want to kind of drive home, where is this all going? So we're going to calculate another Riemann sum just for the general n subintervals. We're going to do this using right endpoints for f of x equals x squared plus 1 from 0 to 2. So I went ahead and drew that here. So from 0 to 2, so let's see. So that's going to be from here to here. And I want to be way more thorough this time with my actual sum. So I want to calculate this as far as I possibly can, actually. So I don't want to just have the setup of the sigma notation. I actually want to do the whole thing. So let's start by using that formula I just gave you. So I'm going to take my formula, so let's write it out. So I'm going to go from k equals 1 to n of f of, actually I'm just going to write the whole formula out to start, and then we'll kind of go from here. So let's see, here's my most general formula. So we'll start here. So where I think you should start is actually by trying to just plug in your A's and your B's just to kind of get a sense of this, and just simplify it as far as you can. Hit play when you've done that. So if I do this, so I plug in my 0 for A, this will be 2 minus 0 over n. So I don't know what n is, so we're just trying to calculate this really general formula. So there's kind of what I've got, and if I try to simplify that just as far as I can, so this is going to end up becoming, let's see, this really is going to be 2k over n, all of that times 2 over n. So I'm going to give you a little warning here. We're going to get a little bit in the weeds with some algebra, and I think this will be the most meaningful to you if you really try to play along and pause kind of in the places where I suggest. So look at this sum here. So remember, our index only has to do with the k's. So I need to take f of this thing. So this is something I have to actually plug into the function. So how do I view this? This would be, I would normally plug in some number for n, right? So I can really view this as a constant. So I can actually just bring this out in front of the sum. So I want to rearrange this like this, and you should do the same. Okay, so look at where I'm at now. So now I've got this. And so what is this asking you to do? This is asking you to evaluate f of 2k over n. So this is now literally plugging 2k over n into this formula. So I think that you should do that and try to simplify it as far as you can, and then hit play. So if I do that, so I'm going to plug 2k over n into this. So where I have an x, I'm now going to replace it with 2k over n. So this is going to be this plus 1, and I'm going to put these square brackets around it. So this is what I actually have to kind of simplify out. So let me clear myself a little space. So I've got a little more space, so I'm plugging just this in. So I need to just simplify this part. So ignore kind of everything else going on. So if I just try to square all of this, so what do I get? So I just leave this 2 over n. This is coming along for the ride. And then if I square this, this becomes 4k squared over n squared plus 1. Okay, so now here's what I want to do. I want to try to simplify this sum as far as possible. So the key to remember here is that you are trying to sum up for k squared, right? You have to remember that n is really something you want to treat as a constant. So using the just algebraic rules for sums, I can now work on breaking this up. So this 2 over n, we're just going to bring that along for the ride for a moment. Now I'm going to put a pink bracket here so that I can just focus on kind of breaking up this piece here. So let me, just so that you're kind of clear what I'm doing, I am now just focusing on breaking this thing up. So this will now be, so first I'll break up the sum. So I've got this 4k squared over n. There's one sum I want to do, and then I have the other one. So this one from 1 to n of just 1. Okay, so there are the two pieces that I want to work on. So now, how far can I simplify these? Well, this I can simplify using the constant value rule. So this guy here, this just equals n times 1. So I'll note that. Now, oops, and I lost my n squared here, didn't I? Okay, so now looking at this other piece here, so remember, we're just trying to sum up the k squared. So this 4 over n squared, this part is just a constant. So I want to rewrite this particular sum, factoring out this 4 over n squared. So remember, this 2 over n right now, we're just kind of letting it hang out. We're ignoring it. I'm trying to just focus on all the stuff in the pink at the moment. So I'm going to factor out that 4 over n squared, and then I've got k equals 1 to n of k squared, and then this other part here, this is just going to be plus n. So that's me using that constant value rule. Whew. Okay, so like I said, lots of algebra here. So now what I want you to do is, you've actually got, you're kind of in a spot now where you can kind of work this out. So I think you should distribute in this 2 over n into this and play around with this. And notice where we've got this sum here. This sum now we can actually express using this formula here. So that's why I told you to have those kind of next to you. So it's a lot of heavy lifting with the algebra. So I think it's really worth your time to try to now simplify this as much as possible. So you're going to have to distribute this into both pieces. So just to be nice and visual here, you're going to distribute this 2 over n piece into both parts. And then this part here, this, let's see, I'll use the blue. This part here, you're going to use that sum formula. So I want you to pause the video and just try to work all of this detail out. And you will see kind of where this is going once you kind of figure that all out. I'm going to clear some room and hit play when you're ready. Okay, so the first thing I want to do is I actually want to distribute this 2 over n. And if you went a slightly different route, that's okay. So this becomes 8 over n cubed times this whole piece. So I still have to evaluate and use that sum formula. This other piece will just be plus 2, right? So 2 over n times the n, that'll just leave me with the 2. So now I can use my sum formula. So this will be 8 over n cubed times, so the formula for this is n, oops, let me write that down, n times n plus 1 times 2n plus 1, all of this over 6. So that gets me to taking care of this part here. And then I still have the plus 2 at the end. So now what I want you to do is I want you to totally just do some heavy algebraic lifting here. Sort this out as far as you possibly can. So you're going to have to cancel out some ends here. You're going to have to simplify the whole top and bottom. You're going to have to FOIL this whole thing out. Work through all that detail and then hit play when you're ready. Okay, so I want to kind of cancel out this n with one of these, and then let's see, I don't want to do too much because I can get lost in my work. So I'm just going to divide also the top and bottom by 2 so I can just rewrite this part. So this becomes now 4 times n plus 1 times 2n plus 1 on top. And then in the bottom, this is over 3n squared, all of that plus 2. So once again, I got to clear some space for myself. So now I can FOIL this out. So I'm going to do that. So I'll just leave the 4 kind of hanging out in the front. So if I FOIL all this out, I get 2n squared, let's see, plus 3n plus 1. All of this divided by 3n squared plus 2. And then I can distribute. So let's see, this will finally be 8n squared plus 12n plus 4, all of this over 3n squared plus 2. And now the last thing that I want to do, I actually want to break this up. So I'll clear some space one more time. So now I'm going to break this fraction into pieces. So this is 8n squared over 3n squared. This is 12n over 3n squared. This is 4 over 3n squared, all of that plus 2. And now I can simplify those little fractions. So this becomes 8/3 plus 4 over n plus 4 over 3n squared plus 2. Now I want to rewrite this 2 as a fraction over 3 so I can combine it with the 8/3. So this ends up becoming, we'll rewrite the 2 as a 6/3. So now I can actually write this in the most simplified form possible. So this is 14 over 3 plus 4 over n plus 4 over 3n squared. Okay. And now you're probably like, what the F are we even doing? So, all right. So here's where we're at. What was that original question again? So I'll remind you. So what we were trying to do was we were trying to come up with a Riemann sum, a general Riemann sum for n subintervals, and we did this using sigma notation. So basically now what I have done is I have come up with the most general formula possible. You tell me how many subintervals that you want, and basically now all I have to do is if I say I want 4 subintervals, well, I just plug in 4, and that would actually, this just automatically gives me that area. So you know how usually we have to, so if I just remind you what we were doing in all the previous problems, previously it was like, oh, I'm coming up with these 4 rectangles, then I'm figuring out their height, and then I'm having to do that, and oh, okay, now I've done 8 rectangles, okay, now I got to do all this work. Well, so what doing this for n subintervals allows us to do is now we don't have to do that anymore. Now it's just tell me how many subintervals you have, and I have this nice simple formula. So even though it was a lot of work to figure this out, now it's like, all right, well, just tell me how many subintervals you have, and I'll just plug it into this, and now I'm done. I don't have to even go through and calculate all those other pieces. But wait, there's more. So here's my question. What happens as n goes to infinity for our formula? So I'll write that down for you. So this was the most general formula we could just find. So what does this even mean if n goes to infinity? So remember, if I go back to my original picture, so let me bring that back. So normally when we talk about Riemann sums, like if I'm trying to calculate the Riemann sum of this little shape here, so think about how clunky this is. We've talked about this before, so it's like I come up with these rectangles. It's just like not perfect, right? Because like it's either going to be too high of a sum or too low. So here's kind of the idea now. I have this really general formula for n. So I could, here's 4 subintervals. So I could just plug in 4 and figure that out. Or I could do, so if I subdivided this again, so now I've got my 8 subintervals. So if I wanted to figure out what's the area of this, okay, well then I just plug in 8. Well, okay, we already know that plugging in like these low numbers gives us a kind of crappy estimation for the area. So what happens as n goes to infinity? From a visual standpoint, what does that look like? So basically, the ideal Riemann sum would be found by like taking the smallest possible rectangles, right? So I just keep subdividing this interval like shown. And I just keep subdividing this thing and subdividing this thing until I have so many rectangles that it basically looks like what I've done is I have just colored in this shape because all of my rectangles are just solid. They're so tiny. The width is like, we can't even tell what the width is. That is kind of like the idea. That would be the ideal. And this would give us like the perfect area estimation. So if I could get n to go to infinity for this, then I would totally just have the area of this shape. And if you remember, the original problem with Riemann sums is it's like, how do I figure out the area of this? Well, now I have this general formula, and how can I make n go to infinity? What method do we have to do that? Okay, we can take a limit. So I can take the limit as n goes to infinity of my general formula. And we know what this is. This is why I love this so much. Okay, so the limit of a constant is just going to be a constant. Now, this, as n goes to infinity, this entire fraction is going to go to 0, as is this one. So this goes to 0, and this goes to 0. So what does this equal? This is 14 over 3. And we have just unlocked the mystery of the universe. How do I find the area of a shape where I can't use a nice geometric formula? Well, you can figure out this Riemann sum, and then you can take the limit of it as n goes to infinity, and there's your area. So the area of this particular shape is 14 over 3 units. So I know that's a really difficult calculation that we just went through, and your head's probably spinning. So you do have this video to kind of watch over and over, but I also have 2 more examples as of this time. Who knows how many more I'll have in the future, but I do have more examples of how to do that last exercise we just did, where I'll walk you through it again, so you've got more to look at. So that covers it for this video, so I'm sure your head's probably spinning, but it's so cool. It's so cool. We just figured out how to come up with the area of a shape where we don't have a nice geometric formula for it, and we did it using calculus. It's so great. Okay, so that's it for this one. If you have any questions, feel free to drop them in the comments. Hey, if you could maybe like this video or subscribe to my channel, I would super appreciate that. And yeah, hopefully I'll see you guys next time.